today let's discuss about how to design TinyURL in a system design interview. So the assumption here is 100 billion meaning short URL per day, and the short URL should be as short as possible. So here is the assumption, and the function requirement would be the user can type in a long URL and then generate a short URL. And also the short URL, when the user type in the short URL into their browser, the browser can direct it to the long URL. So the list user's short URL is the user can check how many URL do they have and which short URL mapping to their favorite long URL. Yeah, basically it's just a short URL mapping to the long URL based on the user. And also the short URL will expire in 1 year. So that is a function requirement. Let's talk about the API here. The post API, the user can send a long URL value to the service with their token. The token is generated by the system, by the login service when the user log into the short URL website. And then the system will return the short URL. Yeah, so that's it. And then the second function is when the user tap into the short URL with their token, and the system, the TinyURL system will return the long URL with a 301, the 301 code. This one will let the user redirect from their browser, or we can say this is a client redirect. And then for this one, we send a RESTful API with a user token, and then the user will get the list of their short URLs and also what long URL is mapping to this short URL. So that is the basic API, and the data model would be, first we have the user model. The user will have a ID, is a unique ID, and also name, email, phone, and etc. And we also have the short URL. The short URL is also have a short URL's ID, or maybe there's a alternative way we can use the short URL value as the ID, because this one is also unique. But in real world, we always will use will keep this ID here, even we have a unique short URL can be as a potential ID there. And yeah, also we will have the long URL value, so which means which short URL map to the corresponding long URL. And we also have a create time and expire time. Yeah, the default value would be 1 year, but we still can, the user can still change this one. Let's say if maybe the user is a VIP, so they can have like a 10 years expire time. That would be more flexible for this design. So as we can see, there are two basic models, and the mapping way is one-to-many. Basically, one user can have a lot of short URLs. So that is the data model and also the API. So let's try to estimate the capacity, the data capacity or something like that, and also the traffic there. So we have the data capacity because every day we will have 100 million URL, a short URL request. And let's suppose each record we use a 1 KB. So yeah, this one maybe we won't use all those things, but for the calculation, make it easier, and yeah, and that won't be a like a buffer for our data capacity. So basically, it's 100 gigabyte per day, and since in this design we will use a cache capacity, we will use a cache. So the cache we can use a like 10% of the total cache there. So the reason is our assumption is like although there are a lot of URL, the active user would just a 10 gigabyte per day. We will store into our cache in order to make the performance better, especially in the latency part. So that's why, but we can change it later if based on our business status. So the write operation, we will have 100 million operation, and so and divide this second, so it's 1,000-second write operation, and let's say the read operation is 100 times than the write operation, then it would be 100,000 read request. So that is the estimation, and for the non-function requirement, because the low latency should be the first priority, because nobody want to wait their short URL wait like 2 or 3 seconds. So that's why the low latency should be considered, and high availability is for our system itself. And for the scalability is if in the future there are more users, so we need to consider scalability part, make it very easy for us. So that is the function and the non-reflection, all those things. So let's go back to the diagram. So this is our client side. It can be a mobile or maybe a web application. Basically, we are using a browser. So they will send a HTTPS to the load balancer, and then go to the API gateway. And API gateway will routing the RESTful request we have already designed for the API part. So let me go one by one for this part. If this is a post request, which means to generate a new TinyURL, it will go to our service, and then the service will get a count generator service. There is a count generator service, which will generate the unique numbers to our service, and in our service, will calculate based on the data, the number generated by this service, and then we got the short URL, and we store it into our cluster. For our cluster, I will use a follower leader for each partition, and also we have to partition this part in order to make our service performance better. So in this way, we will choose a NoSQL DB because as we can see for the short URL, there are a lot of things we can store here, and because the data capacity is 100 gigabyte, so the per year would be very huge. That's why we use this one, and we don't want a hot spot part, so that's why we use a partition to distribute the traffic, the write traffic, or maybe the read traffic. So yeah, so that is this part, and for this part, we use a little follower. The reason is because we have 1,000 read operation, but we have 100,000 read operation. So in this way, the leader can only take the write operation, and the follower we can scale out more follower to support the read operation if we read from this cluster. So yeah, so that's it. For the partition key, I'm using the short URL as a partition key to distribute the traffic into the cluster. And yeah, so this is that part. And for this part, for this API, because the user want to get the short URLs from this cluster. But right now we are using the partition, we are using the short URL as a partition key. So in order to accelerate this query, we will use a secondary index to do that. The secondary index can, let's say without a second index, if we want to get a particular user's short URLs, we have to go to all the partitions to get the user's URLs. Even maybe in that partition, there's this particular user's information, this particular short URL information. So by using a secondary index, we can make the performance is better, both for the user's latency part, because our system just go to this user's short URLs partition, and and also for this one, there's also a trade-off, because when we generate the short URL and try to store into this cluster, into this DB cluster, we have to generate a secondary index, and which will make the which will take a longer time to generate. So that is a trade-off, but for our requirement, that should be fine. The reason is when one user generates a short URL, they can wait for more second, because it's not what they are using the URL, the short URL to get the target website. So that part should be fine. And so that is about this part. And also, let's talk about the get part. This one is our core functionality in this system. So when we hit this service, routing by basically it's routing by the data gateway, and we will go to the cache. So the cache is store a key value. The key is the short URL, and the value is the long URL. And because we also support a TTL, I mean the expire time, so we can set the TTL there. The default TTL would be 1 year, and since all those information is here, so we also there would be a single point of failure, right? And we have to use a replica cache to store to prevent maybe there's a single point of failure for this cache. As we can see, the cache capacity is a 10 gigabyte per day, and so let's say we have 400 days, and let's say we have 400 days, and each day we will generate 10 gigabyte. So this is a total 1 year's gigabyte there, and that's why we need to a distributed cache, which means we also have to do a partition to store the data, to store the key value pair, which is short URL to long URL mapping, and also because each cache cannot handle 100,000 QPS, so we have to partition that. That's the reason we have to partition that. Basically, for the read operation, or we can say the QPS, and also for the storage reason, we have to split it. So by using a partition technique, so the partition is still the same with this cluster. We will use a short URL to do that. So in this way, we are okay to make sure our system is working. So here's all about the system. So I'm gonna talk about this one, the strong consistency data. So we will use a basic 2, and the URL's length, because we want URL as short as possible. So I'm gonna use a 7 character there. The reason is how can we generate this 7 character? So let's say we have several service, and here is the count generator. Let's say it's a CG, right? And it's the straightforward way is every time each service will take 1,000. This number is just estimate. We can take 2,000. That should be fine. So 1,000 number. Let's say this one is from 1 to 1,000, and this one is 1,001 to 2,000, and so on and so forth. So in this way, for this service, when we generate the data, we will use a base62 algorithm to generate those data, to generate the TinyURL. And for this one is the same, and this one is the same, because before these 3 services, there's an API gateway and a load balancer. So the first request will go to here, and then let's say we are using we are using one by one this technology. So for this one, it will generate a thousand. Maybe this is user one, and this is user two, and this is user three. So it's okay. We can distribute all the traffic, and meanwhile, maybe the hacker cannot guess the next URL by looking by using maybe some random URL generator to try to guess what's the rule over here. So in this way, we also prevent this the bad user's behavior. And maybe you will have a question. Let's say if this machine is down, right? So what we will do? So we just lost everything because all those numbers are just stored into this service. But that should be okay. When we add a new machine, or maybe this machine is a bug, we just get the like 3,000 to 4,000, which means we just throw it out. We just we don't care about that one, because we can still get a new data from the counter generator. So in this way, we still can generate a unique URL, and because we are using base 62, so we can get the 7 lines URL, and if we calculate, this should be a very large number, and it's good enough for our service to use. And here, how do we generate this the data, right? There are two approaches we can use. One is we can use a data generator like the zookeeper. We can use it to generate like the range part. And also we can use a DB, just a SQL DB. The reason is very straightforward. So let's say the initialize is 1, and then this this service try to get 1,000 whatever, 1,000 number. First, it will check the DB is 0 and then update it like 1,001. So this service still do the same logic, because every time when the service handle 1,000 requests and then go to this counter generator, basically we can calculate how much the rate. So basically we can see the read operation is this number is 100,000, because every 1,000 data we will go to the counter generator service. So this service QPS is only 100. Yeah, it's only 100. So that should be totally fine for this one. Either we can use a zookeeper, or either we can use a DB. Let's say if this generator is cannot handle 1,000, right? We can every time take maybe 10,000 the data generated by this data generator, and then serve the TinyURL part. So this is how can we generate both a unique TinyURL and also can use either zookeeper or just a SQL DB. Both are okay. So that is the whole solution here. Yeah. So thank you for watching. Yeah, that's it. Bye.